This is the walkthrough video for PCTC 2023, question 8, gem spirals. Okay, so this question seems pretty difficult at first, and it is pretty difficult because there are loads of different edge cases or loads of different conditions that you have to code for. However, I'm going to show you what I think is a pretty cool and nifty way of solving this without needing to account for all this infinite if statements that you might otherwise have to write. Okay, but what is the question? So we're given this grid, and we basically just want to start in the top left corner and spiral inwards until we've gone through the entire grid. And we need to calculate what is the maximum number of, like, what's the maximum fuel that we need, or the maximum size of the fuel tank that we need. Each movement takes one piece of fuel, 1 unit of fuel, and every time you reach an at symbol, then you've refilled your fuel tank. And so you essentially just need to figure out how many gaps there are between each at symbol. Now, there might be a fast way to do this, but I've noticed in the constraints, we only need to go from like a maximum of 64 rows and 64 columns, which is not a very big number. 64 times 64 is not very big for computers. And that means we can probably just take the more intuitive route and just simulate this spiral. Again, there may be a faster way, but I'm just going to simulate the spiral, and that should be good enough. Okay, so let's do the easy bit, which is taking in our inputs. And what's the first number? That's the width. So width is going to be int input. Oops. Height is going to be the same thing. And now, what's our grid called? Okay, let's just call it grid. And oops. And let's just do this on one line actually. So I'm going to do a list comprehension. So let's take in an input, and we'll add that to the grid for as many times as there are rows. So this will basically just write so these 4 lines of code basically just take in all of our inputs, and it creates the grid, and the grid is a list of strings, and each string is the row that we're looking at. Okay, now what do we do? Okay, let's have an infinite while loop for now. We might be able to change this later, but for now, let's keep it infinite. And what we want to do is we want to write the code that just keeps on moving our car or our thing in a spiral position throughout the grid. So how are we going to represent where we currently are, and how are we going to represent the direction we're moving in? Because our direction initially starts off as going right, but obviously at some point you have to change to go downwards, and then you have to change to go left, and then up, and then right, downwards, left, up, right, and so on. So we need to keep track of the direction that we're currently moving in as well as our position. So one way you could do this is with complex numbers. Now this is quite difficult, and pretty much everyone seeing this video probably hasn't come across complex numbers before. But what complex numbers are is they're just a way of representing almost 2 numbers in one, and it's just a different number system to the normal number system that we use from 0, 1, 2, 3, so whatever. The complex number system is made up of 2 parts. Each number is made up of 2 parts. There's the real part, and then there's the imaginary part. The real part is just like a normal number. The imaginary part is also just like a normal number, but in Python you add a j to the end of it, and that just symbolizes that you have 2 parts. So you can kind of think of it like a complex number is effectively just 2 numbers put into one number. So it's just a different way of representing numbers. Okay, so, I'll explain things as I go along, so hopefully it makes a bit more sense. So what's our starting position? Our starting position is the top left, which we're going to call coordinate 0. And then the coordinates we're going to say extend outwards to the right and downwards to the bottom. So our starting position, or I guess our current position, is going to be equal to 0 plus 0j. And so what this code does, like this is a complex number. There's a 0 and there's a 0j. This is called the real part. This is called the imaginary part. So both the real and the imaginary parts in this case are equal to 0. But again, this is just a way of storing 2 numbers in one, right? We're storing that number and we're storing that number in one variable. And we'll see why this is useful very, very soon. Okay, now let's store our direction. And our direction initially is going to be rightwards. And that means we're going to go, if these are our coordinates, the 0 and the 0j, and if the 0 represents our x value and the j represents our y value, then going rightwards just means you're doing that. Because you're increasing the real part by 1, you're increasing the x value by 1. And so that's the direction we're moving in. And that's our current direction at the start of our code. Okay, what else do we need to do? We need to keep track of what we've already visited. So let's create a visited set. And this will just make sure that we don't revisit the same points, because every time, well, we're just not allowed to revisit a point basically, because that's what the question says. Is there anything else we need to do? Not for now. Okay, let's make sure I spell correctly. Okay, so the first thing we want to do in our while loop is check if the cell you're about to land on is outside the bounds. So the cell you're about to land on either doesn't exist or is a cell you've already visited before. That's when you switch direction, right? And I think it actually says that explicitly somewhere here. It says, let's see, turning right whenever you reach the end of a row column, so whenever you reach the outer bounds of your grid, or just before you reach a location that you've already visited. So essentially, if our next move is going to be invalid, let's change the direction now before we actually do that move. And so how do we check if it's invalid? Let's just say if our next move, which is going to be current plus dir, because if you think about it, if we want to move right, we can just add current and dir. And this is the power of complex numbers, right? When you add two complex numbers together, it adds the real parts separately and it adds the imaginary parts separately. And what that means is when we add, for example, 0 and 0j to 1 and 0j, our answer to that is just going to be 1 and 0j. It only adds the real numbers, so the numbers on the left, and then the numbers on the right, completely separately. And that means we can kind of add 1 to each of our x and y coordinates as we please. So for example, if we were to do -1, it would just -1 from that. Or if this was our thing, then current plus dir is going to be equal to -1 plus 5j. Right, so you see the pattern here. And this is useful because it means the next position on our grid is just going to be equal to the current position plus the direction that we're going in. And now we can check if that's invalid. So if we've already visited that, so if that's in the visited set, then it's invalid. Or it's also invalid if it's out of bounds. Now, this is a slightly harder bit because you can't check whether x and y are both out of bounds. You can only check whether the x is out of bounds or whether the y is out of bounds. So we need to find a way to specifically get the real part of this complex number, and the real part of this complex number, and the imaginary part of this complex number, and the imaginary part of this complex number. And just to repeat myself, the j is just a way of indicating that this is called the imaginary part. The j isn't actually part of the number, right? It's just how Python treats it. Because if we don't have the j, for example, Python sees this as 0 plus 0, which is just equal to 0. So that's what Python's going to do. But we want to make sure Python knows that we want to keep both zeros separate from each other. And same here, we want to keep the 1 and the 0 separate from each other. So we add the j just to say, this is a complex number, keep both numbers separate. Okay, so we want to check if the real part of the x-axis or the x-coordinates are out of bounds. And so to do that, let's say if current dot real plus the dot real, and so this dot real way is just this dot real command is just a way of accessing only the real part of the numbers, only this first part or the x-coordinate. So if when we've added them together, then it's so let's actually add a not in front of it. So if it's not within the correct bounds, what are the correct bounds? Well, it should be bigger than -1. I guess let's do bigger than or equal to 0. And it should also be smaller than or equal to, actually no, it should just be smaller than, this is the x-axis, so it should be smaller than the width, which is w from our first line of code. Right, so all we're doing here is checking to make sure that we're within the bounds of our grid. And let's just do that again, but for the other axis, so the imaginary part. So if the current imaginary part, which we refer to by using image, and the plus the direction of the image, so the image of the direction part, if they're not within this range, then it's also out of bounds, and therefore we need to change our direction. So this chunky line of code, all it does is basically just check, is our next move invalid? And if it is invalid, before we take the next move, let's actually change the direction. And now this is where the real cool part of imaginary numbers comes in, because so far, everything we've done, you can kind of just like almost do as a list, right? You're probably saying to yourself so many times, or you're probably screaming at your computer right now saying, Suresh, why on earth do I need to use an imaginary or a complex number to hold two numbers? When what I can do, for example, is this. If I can just use a list or a tuple to hold two numbers, why am I bothering to use an imaginary or a complex number? Sorry. And obviously one reason is that this is just a bit nicer. You can literally just add the two numbers as opposed to, for example, doing current 1 plus dir1, it's whatever. But the main reason we're doing complex numbers is it means that to change direction, all we need to do is that. And I'll explain what this does. So if we look at the changing in direction, we're always changing direction by rotating right by 90 degrees, right? Every single time, because we're moving in a spiral. So we move forward, we go right by 90 degrees, we move forward, we go right by 90 degrees, and so on. This turning by 90 degrees clockwise just keeps on happening. And that means that instead of having to like have a ton of if statements here to figure out what's our current direction and what's our new direction going to be, we can just take our current direction and rotate it by 90 degrees. And because we're dealing with complex numbers, this will work. So by multiplying our direction by 1j, or 1j really just is an imaginary number of 1, by multiplying our direction by that, we rotate our direction by 90 degrees. I won't go into the maths of this and how this works, because this is quite complicated and it's complex numbers. It's called complex numbers for a reason. But this system is a useful one to remember. I know before I knew what a complex number was, I actually learned this coordinate system because it could have been useful. I never actually used it, right? Because I was too scared to. But I would say learn it, right? Because even if you don't understand how it works, you can kind of understand how do I rotate 90 degrees, how do I rotate left 90 degrees, and all of those basics. And that means that you can then use this coordinate system as you go on your Python journey, and it's usually a bit faster to code, especially in competitive programming environments. Because all we're doing here is just rotating by 90 degrees. As we've rotated our direction, and what this actually does, this changes both the real and the real and the imaginary part of our direction, right? So if we were to, for example, up here, if we were to multiply that by 1j, our new direction is now going to be, I think it's going to be 0 and 1j, right? So what this does is we've now switched our direction to, instead of going rightwards, which is what the 1 represents, we're now going downwards, which is what this 1 represents. And so that is like our coordinate system in action. And that's why complex numbers are epic in coordinates. Okay, I think that's pretty much all the complex number stuff done. Hopefully that didn't confuse you. If it did, then try and use the logic that we covered so far, because the logic we haven't used is too complicated. So try and use that logic. And if you really want, you can program this as, for example, a tuple that I described earlier, or a list. But it just means that this if statement and then the lines of code right under the if statement are going to be much longer and a bit more complicated than what we currently have. It's going to be less clean. Okay, now let's get on to the rest of the code. So what do we want to do? That's a good question. We want to, so we want to check if our current cell, no, we want to add our current cell to visited before we do anything else. So let's take visited and add our current cell or our current coordinate system. And that just to keep in mind, like remind you, we're doing this because we need to ensure that we don't visit a cell twice. So let's just add that cell now. And the next thing to do is to check if our current cell is actually an @ symbol, right? Because if it's an @ symbol, then we need to reset our fuel. So if, so we basically need to extract the x and y coordinates of our current complex number equation and use that to reference the right cell in grid. So if grid current and dot real and then current dot imag. So again, just to remind you, the real part we're saying of the current variable, we're going to say that refers to the x coordinates and the imaginary part refers to the y coordinates. So actually this should be the other way around because Python does x and y oppositely. Yep, so now what we've done is we've kind of converted our complex number coordinates into finding the actual string or the actual symbol that's at that coordinate in our inputted grid. And so we're going to say if that's equal to the @ symbol, then we have to reset our fuel consumption. But we haven't actually kept track of our fuel consumption, so let's do that here as well. So let's say fuel starts off at 0, because obviously we haven't moved anywhere, so like fuel is 0, we've used 0 fuel. And every time we move a cell, we want to add 1 fuel. And so we'll deal with that later, but for now, let's reset our fuel here. So let's set fuel equal to 0 every time we encounter the @ symbol. And now we've dealt with, so up until now, we've dealt with everything related to our current cell, right? We've dealt with whether our next cell is invalid and therefore we need to change direction. We've dealt with adding our current cell to the visited set, and we've dealt with checking if our current cell is, what are these called? Gems. Yeah, it's a gem. I think it's a gem. Yeah. Power gem, sorry. Okay, now let's actually move ourselves, right? Or move our car or whatever. And to do that, as we said before, literally all we need to do is just current plus dir, because that's how complex, that's the beauty of complex numbers. And so it's going to be current plus equals dir. And we should also probably add our fuel by 1, right? Because every time we move one cell, we increase our fuel usage by 1. And so that's what we're doing here. We're increasing our fuel usage by 1 by moving to that cell. And we also need to know when we should break out of this while loop. And we should break out of the while loop when we visited every single cell or every single coordinate. How do we know if you visited every single coordinate? Well, if you go back to the beginning, we actually inputted the width and height of our grid, which means the area of our grid is just width times height. And that means width times height is the total amount of cells in our grid. And since visited is a set that looks at every cell we've already visited, we can basically say if the length of visited is equal to width times height, then we have visited every single cell and we're done with the code, right? Because, I mean, that just makes sense. We can, of course, also kind of put this up here if you want. So we can say if len visited is not equal to every cell that exists, then we keep repeating this code. But I think that looks a bit messier, so I'm just gonna do that. Okay, and the final thing we need to do is keep track of our maximum fuel usage that we've used so far, right? Because it only wants us to output the maximum amount of fuel we need in the entire journey. So at what point in time do we have our maximum fuel usage? Well, let's just keep track of our maximum fuel. So let's create a new variable called max fuel. Let's set that equal to 0 to begin with. And as our code runs, let's add, every time we're on a cell, let's change max fuel to be equal to itself, or the maximum of itself, or the current fuel that we're using. And at the end of our code, we can just print max fuel. And the reason, like what we've done here on line 18, the reason this works is we're constantly updating our variable called max. Every single time we move, we're updating our variable called max fuel, and we're updating it to either be itself or to be, I made a typo, to either be itself or to be the current fuel usage. And it chooses whichever is the greatest value, right? Because we only ever want to store the greatest value. Because as we progress through our spiral, we might get lower values than one we've already encountered. So for example, max fuel might be 9, but then we might encounter 6. We don't want to update max fuel to be equal to 6, because max fuel should be the maximum fuel we've ever used. And so we're going to keep that as 9. And so this is a cool trick to do that. That doesn't get us 10 out of 10. What is the issue? Runtime error. This is probably a typo somewhere. Max fuel. Fuel plus equals 1, current plus equals dir, len visited, current plus dir, current. Okay, I have no clue what this error could be. I don't know if you've seen it, you're probably screaming at your screen right now. But let's just do a practice input and see what it tells us. List indices must be integers and slices, not floats. Oh yeah, sorry. So when we take only the imaginary part or only the real part of a complex number, it automatically gives it to us as a float, which is quite annoying. So we just have to convert that into an integer here, because we want integers. And now that should be able to work. But yeah, I would say just keep in mind and remember this idea of using complex numbers as a coordinate system. I mean, you obviously don't have to, but I think it's quite useful. And hopefully this code makes sense. Now, here we got 10 out of 10, but I'm pretty sure that some of these test cases are actually like really random edge cases. And so if you coded this and maybe you got like 7 or 8 out of 10 or even 9 out of 10 and you're watching this video because you're confused, chances are you've probably just like missed off, like your ordering of all of this logic is probably wrong. For example, if I only checked my maximum fuel every time I've reset myself, I don't think I'm going to get 10 marks because, for example, you might have a maximum fuel once you reach the center of the spiral. So the center of the spiral might not have a power gem, but you might still just use like a billion fuel units to reach the center of the spiral. But your code only checks to update max fuel if we've encountered a power gem. And so that gives us an error. Yeah, I don't even know why that. Oh, right. Obviously, the error is because of that. But yeah, so just keep in mind the ordering, right? Because you need to make sure that you actually do account for every random edge case. And if your code doesn't work, but it looks kind of similar to mine, it's probably just a very slight thing like the ordering or whether your max fuel code is in the wrong place. Like it should be up there. Yeah, but you only got 8 out of 10 by putting it in there because of the edge case I just described. So yeah, be careful there.